Action.
Welcome to the Tubaldi Lab. I'm Eleonora Tubaldi, Assistant Professor in the Department of Mechanical Engineering at the University of Maryland, College Park, and Director of the Tubaldi Lab. So in structural mechanics, mechanical instabilities have been traditionally considered the onset of failure for structure. So if you think about a beam and you compress it axially, at some point the beam is going to buckle one way or the other, and it's going to be really difficult for the structure then to go back to its original configurations, right? Oftentimes the structure is going to break because the buckling instability results in large reconfigurations of the structure. Now, in our lab, what we try to do is to leverage mechanical instabilities and the large reconfigurations that the structure experiences in order to achieve new functionalities. So we can think about soft robots that can be actuated with mechanical instability within them. We can think about wave transmissions within mechanical metamaterials in order to send signals in the directions that we want. So in our toolbox, we have the buckling instability and also the snap-through instability. So the snap-through instability is based on the multi-stability or at least bistability of our structure, where we have two energy wells. And with this instability we're going to do, we're going to jump from one energy well to the other one. To further explore the wonders of mechanical instabilities, I will pass it to Michael, PhD student in the Tubaldi Lab.
I'm Michael. I'm a PhD student here in the Tubaldi Lab studying mechanical metamaterials. So in the context of mechanical instabilities, if I'm interested in knowing what state is the structure going to go to, I first have to know what state can the structure go to. And one of the fundamental ways we look at that is either through a force perspective or an energy perspective. So if we take perhaps a ball in free fall, we're probably pretty familiar with writing out the force balances. You do the sum of the forces equals the mass times acceleration. Another perspective to have at the system is looking at it from an energy perspective. And they're both equally right in their own methods. It's just a different way, a different perspective to look at the system for. So one great simple example we can look at is, imagine I have a ball on some potential energy curve that looks like a hill. And it's a great example because whatever hill you put the ball on, the potential energy is going to be exactly proportional to the height of your hill. So if this is my beautiful rolling hill here, and I'm interested in what are the stable states that a ball placed on this hill could end up in, a great way to visualize it is just imagine if I were to put a ball on the hill and then let my intuition take over and see what's going to happen to the ball. Well, if I put the ball on the side of the hill, it's going to want to roll down. It's going to want to roll down into the valley. And so we would describe this valley as a stable configuration. And any other spot up on the hill here would be unstable because the ball is going to want to roll down to a valley. We can then, from an energy perspective, you can show me a graph and we can intuitively find all the stable configurations because stable configurations will be energy minimums or local minimums on the potential energy plot. So on this plot here, we can see we have one stable configuration, which would be the ball at the bottom of the valley. But it's very easy in metamaterials to make arbitrarily complex potential energy landscapes. So take this more interesting landscape where I now have sort of two valleys and one peak in the potential energy landscape. If I'm interested in finding stable configurations of it, again, I'm interested in finding local minimum, and I see I have two local minimum, sort of one here on the left and one here on the right. And if I picture a ball in either of these wells, I can picture it being placed there, and it's not going to want to move as opposed to if I place it on either side of the well. Then an interesting question is, well, I don't want to just place a ball in a well and have it stay there forever. I want the ball to travel the valley. I want to see both sides of the valley. And so I'm interested in how does the ball move from one stable configuration to the next. So if I'm old Sisyphus down here at the bottom of the well and I slowly start adding force to my ball and I slowly move it and push it up the hill and push it up the hill and push it up the hill, I'm gonna have to put energy into the system, which I observe that, or I can see that by going from a lower potential energy to a higher potential energy. That energy came from in the form of me pushing the ball up the hill. But once I get to this peak, an interesting thing's going to happen once I move a millimeter to the right of the peak. All of a sudden, gravity is going to want to help me out, and the ball is going to roll on its own accord down to its other stable configuration. And then from an energy perspective, we can refer to this as snap through. But it's this first understanding of what are the stable configurations the ball could be in, and then next understanding how do we move between the stable configuration that gives us a very powerful insight into mechanical metamaterials.
We previously talked about the snapping of arches, but where did the idea come from? So, arches are all around us as a structural element. If you think about the Colosseum, that's an array of arches with a beautiful outcome that can withstand large loads. Now, the question is, everything there is static. Now, how can we make things dynamic? So how can we make things move? So arches, since they are bistable, we can arrange them in a mechanical metamaterials in a way that we can transmit waves and signals through it. We can have wave steering capabilities, and this makes this arch able to snap very interesting elements to tessellate them. So they are very simple in their structure, so we just need to connect them. So compared to previous metamaterial designs where the snapping elements were very complex, in this case now we have a simple array of arches that is able to reconfigure itself with a wave transmission going through. So to further talk about arches, now I'll pass it to Michael.
So one of the powerful phenomenons of the single arch is the snap-through phenomenon, which is the rapid transition between stable states. So I have my buckled beam right here. It has two stable states. It either wants to be upward or it wants to be downward. And I can see the snap-through phenomenon when I transition between the two states. So what I'm going to do is I'm going to start with the arch initially downward. I take my finger and I'm going to slowly push on it. As I push on it, I'm adding energy to the system until there's going to be some critical point where the arch wants to move away from my finger and all of a sudden snap through to the other configuration. And we can see that in the potential energy. When I start the arch downward, I'm starting in a stable configuration, so perhaps that corresponds to this stable well right here, where the arch is stable and it's downward. The way I add energy to the system is I take my finger and I slowly push on it bit by bit. And then right here when it crests and it's just about, just at the peak of the potential energy and it wants to jump to the other one, that's at the point where I'm just barely balancing the arch here, and if I move my finger a little bit more, it's going to snap through down to the other stable configuration, which corresponds to that one. And we can do snap through not just with a single element, as fun as those are, we can do multiple elements connected. So here I have a simple one-dimensional chain of arches connected to one another, and now when I impose the snap through phenomenon of the first element, because each of these arches are connected to their hinges, it's going to force its neighbor to move. So here when I push on the first arch, you can see that its neighbor arch transitions from down to up, which causes its neighbor arch to transition from up to down. And it's a repeatable process. I can send mechanical waves through. And we're obviously not limited to just one-dimensional spaces, but whatever your imagination can think of. And so in terms of mechanical metamaterials and their application, there's two broad ways you can divide it. You can either divide it into categories of either I'm interested in the environment controlling the structure, or I'm interested in the structure controlling the environment. So an example of that first one, where I'm interested in the environment controlling the structure, perhaps that would be if you make an aircraft wing out of bistable materials that can reconfigure based on the flow speed, or the speed at which your plane's going. And perhaps you have an aircraft wing made out of here and you reach a certain velocity that all of a sudden the wings reconfigure and you fly more efficiently. And on the other side of the things, the other side of that is where the structure controls the environment, people have made fluidic fuses out of the bistable arches, where upon a critical flow rate, all of a sudden the arch reconfigures, diverts fluid flow, and perhaps saves sensitive microfluidics. But that broad category of either trying to control the structure with the environment or control the environment with the structure, the possibilities really are endless. We do applications with thermal and we do applications with mechanical signals. And it's really however you can come up with controlling the structures, the metamaterial could allow you to do it. So when we study mechanical metamaterials, we're interested in the mechanical properties of metamaterials. And metamaterial is a portmanteau of meta, which is the Greek root for beyond, and material. And metamaterials are described by structures whose properties who extend beyond its constitutive materials. And so the way you make a metamaterial is you take a unit cell or a building block, you repeat it over and over until you end up with a metastructure. Now, the classic example of a metamaterial is if I start with a rubber block, maybe a pink rubber eraser, and I squeeze the block. I expect the size of the block to go outward if I squeeze it downward, and in engineering we refer to that as the Poisson's ratio. And with metamaterials, you can actually devise a structure that has a negative Poisson's ratio, which is something that you would not possibly be able to get with traditional materials alone. There's so many different types of examples of metamaterials. Really, any choice of a unit cell and how you repeat it, you can form a new metamaterial. So for the case of our arch, we start with a single buckled beam and we repeat it into different geometrical shapes, either squares, hexagon, rhombuses, or so on. And based on our choice of material for the arches, but also based on how we arrange the arch, we can get different mechanical properties that extend not just to the arch, but to the metastructure as a whole. Now, to understand metamaterials, you have to have a really good understanding of the math behind it. And to that, I'm going to turn it over to Kieran, who's another graduate student in the Tubaldi lab.
All right, for any complicated engineering problem, the best practice is to start by defining everything you know about the problem. So let's do that. For our structure, we know we have an arch of length L, as well as some known material properties, including the Young's modulus E and the moment of inertia I. Additionally, we know we have two boundary conditions, one pinned and one roller, and we're applying a load of magnitude P along the center line of the arch. Additionally, we're going to define any deflection as the term W, which is a function of X, the X position along the arch. The other thing we know about this problem are the four boundary conditions. We know that at the beginning and end of the arch, we have no out-of-plane no vertical deflection, and we know that we have no moment at the two hinges either, or no curvature, which is how we're going to define it later on. Now, when we solve this problem, we're going to use Bernoulli-Euler beam theory, which looks to model the arch as a fourth-order differential equation. And we can use some classical ODE solving methodologies in order to get the deflection which is shown here, as well as all of its derivatives shown below. And the interesting thing to take away here is that we have four unknown coefficients, A through D, in this equation, that when combined in different magnitudes give us different deformed shapes of the arch. In order to figure out what those four coefficients are for our problem, we need to plug in the boundary conditions that we defined earlier on. And there are two cases that we can really see when we do this. The first is the so-called trivial solution, where all of the four coefficients are equal to 0, and as such, we get that the deflection is equal to 0. The more interesting case, and indeed the one that gives us the stable solutions for our other solution approach, is the non-trivial solution. And in order to do this, we need to have that sine KL is equal to 0. Now, this is a particular condition that requires us to have particular values of the applied load P. In order to find those values, we can substitute in the value for K, and we can get the critical buckling load, which is shown here. Notably, the critical buckling load has the term N, which is the integer value, which can go from 1 to so on and so forth. And when we have this critical buckling pressure, we have a corresponding deformed shape, which is defined here as W sub N, which again, we can define for different values of N. Together, all these values of N will define any different deformed shape of the structure. However, when we're looking into our buckling problem, N equals 1 would have the lowest critical buckling load, and so we would always see that one first in practice. All right, so the mode shape we're specifically interested in is for N equals 1, which is shown up here. Now, notably, we haven't made any assertions about the magnitude or sign of the unknown coefficient C. And indeed, we can either see that C is greater than 0, for which we get this upward-facing sign shape, or we can have that C is less than 0, for which we get this downward-facing sign shape. If we were to plot the magnitude of this unknown coefficient as we increase the applied load P, we would see something like this. Initially, as you increase the applied pressure or applied load, we get this spring-like behavior, where the arch just shrinks along the center line. However, once we reach this critical load P crit, we have that the valid solution, or the stable solution, now splits into these two paths, one for which C is greater than 0 and one for which C is less than 0, because it's no longer stable for the structure to continue shrinking along that center line. This shape of the graph is known as a pitchfork bifurcation, and it appears a lot in different buckling analyses for different structures. Now, we can think back to the energy well approach that we saw earlier on, and we can see that these two energy wells correspond to the two different solutions that you get when you hold the arch in place with a particular value of the critical load. And indeed, once we do this, you can imagine the ball on the hill. If we apply not quite enough pressure in order to get the ball over this hill, then the structure will revert to its original shape because this is a stable configuration. If indeed we apply a high enough force to crest that hill, we can snap it over the top and have it go to the other stable shape. This type of force-based analysis is also really useful because it's not limited to arches. It can be used for many different shapes and many different geometries of shells. Mechanical instabilities were in our minds as we were thinking about our research, more specifically our research into soft robotics. Soft robots and mechanical instabilities often go hand in hand. When we think about soft robots, we often think of devices that are very flexible and can conform to their environments. However, this often comes at the cost of actuation speed and actuation force. In contrast, mechanical instabilities can make up for these shortcomings because they're able to produce rapid deformations or release high amounts of energy during events like snap-through. These can make up for some of the limitations that soft robots classically suffer from and enable us to push the boundaries of soft robots, and more specifically our soft grippers, in order to develop devices that are able to adapt to objects and conform to complex surface geometries, protect them as we manipulate them and move them around, and safely release them, as well as leading into some of the sensing capabilities that the grippers demonstrate as well. Whereas the arch is an example of a thin beam, we can also see buckling in structures that are thin shells. For the arch, it demonstrates its ability to buckle because of its symmetry across its center line. But for this structure, a thin hemispherical shell, it demonstrates its ability to buckle because of its radial symmetry. And instead of applying a compressive axial load, we apply a uniform pressure to the entire surface of the shell. Finding the resulting buckling mode shapes is a lot more challenging in this case because of the added complexity that to the governing differential equation that going to a shell adds. So for this case, we use finite element methods in order to find the buckled mode shape. And when we do this, we see that the buckled mode shape of the structure is this two-lobed pinching mode shape that we call the Pac-Man shape that gives us the grasping shape that we're looking for. One of the other exciting things about using soft materials is the ability that they give us in order to react to external stimuli in the environment. More specifically, if the Pac-Man gripper comes into contact with an object in its environment, it's going to deform because it's made of a soft material. And because the gripper is hollow and it has a pneumatic cavity inside, we can monitor these deformations in a way using a pressure sensor that watches the air pressure inside the gripper. Now, when it comes into contact with objects of different sizes and shapes, the pressure response is going to be different. Not super different, so qualitatively, if you just look at the plots of the pressure, it might be challenging to discern which object is which. However, if we use machine learning techniques, we're able to predict the size and shape of different objects with over 95% accuracy. Now, we've talked a little bit about the Pac-Man gripper as well as the snapping arches, but we have one final project that we'd like to talk to you about that includes both soft materials and mechanical instabilities.
Another project in our lab that's a combination of metamaterials and mechanical instabilities are the sponges. This is a metamaterial made out of a rectangular array of these cylindrical shells. And by pressurizing the connected internal cavity, we can actually buckle the shells and get the cylinders to close. One thing we're interested in doing with that is swimming and using that closing motion to propel water to get the sponge to swim forward. Another example we can do with this is achieve a level of programmability. By increasing the thickness or controlling the thickness of the cylindrical shells, we can control the pressure at which they buckle. And we can use that for making a selective gripper. We can selectively grip one row of items or two rows of items or both of them. And now that you have an idea of what we've been working on in the lab, I'll hand it over to Dr. Tubaldi to talk about what the next steps in the future for the lab is.
In the Tubaldi lab, we're also studying cardiovascular biomechanics problems like aortic dissection. So we're interested in developing predictive models that help us understanding when the bulging, so the potential aneurysm, is going to rise within the arteries. In the future, we also would like to explore avenues to leverage mechanical instabilities and mechanical metamaterials for the design of cardiovascular prostheses to develop the next generation of cardiovascular grafts. That's our story. Researchers investigating the magical world of mechanical instabilities and metamaterials, always pushing the boundaries and asking ourselves, which boundary can we push next? And how can we think differently? Now, what boundary will you push by thinking differently?